Hello, everyone. Back again to finish up on our previous stream of going through the Insomni'hack Teaser 2019 Challenge onewrite. And where we were last time is we were leaked the stack and the PIE addresses there, and we were able to then redirect control flow. But the question and the problem that we were struggling with is where to go from there. So what address actually to then overwrite? And so what I did basically since the last time I was on here is I went through and I re-looked at this binary. So this is the onewrite binary, and I was hitting this problem where some of the write-ups I was reading were saying like, okay, well, you can overwrite the Finney array. And so the idea being there's two elements in the Finney array, and so each of those is a function pointer. So the idea being you overwrite the last one to jump to do overwrite, which gives you an arbitrary write primitive. Then you use that to overwrite the second entry in the Finney array to put you back to starting at the start of the Finney array. So basically you create this super sweet infinite loop here where you're going to go back to the start every time. So this is what I realized that the problem was. And so what I'm going to do now is basically try to fix this. So we have our exploit here, so we could briefly go through it. We are leaking the stack, so we're reading until we get that, and we're leaking out the address on the stack, and then we use that in order to call into the so once we get the stack address, then we use the overwrite to change do leaks RIP the last byte to be 04, which then jumps back in, I believe it was main. Let's check here. I don't know. I just looked at this briefly over the weekend. So let's see. Yeah. So 04, changing do leaks. Hello. So then we're going to call into 04, which is going to call do leak again. And this is what then then we leak PIE. So we leak all the memory addresses here. And then there we go. Then from there we get that. So this leaks out the address of do leak. So now we know both all the memory addresses on the stack and the memory addresses on the heap. The memory addresses on the stack and the memory addresses of all the PIE binaries. And then what we're going to do is, so we set that up to then the exe that we loaded in, we then rebase all the addresses based on what we get. Then we overwrite the Finney array entry with, this is the last time we did this, we tried to go to start. So let's go there. So now we can try this bad boy. So here's, I'm not on the right virtual env. So we run this, and then now here, so it's breaking at the start. We hit continue. It's going through our exploit. It should get to this interactive part here, but we've hit a problem in that this causes a seg fault. So what we're going to do now, so this is what my original idea last time where we ended was, hey, let's just jump back to the underscore start, which is literally the entry point of the function. Hopefully that would like set things up, but it causes some seg fault probably because things are already caught up, and so there is no real need for that. So that ended up not working. So what we're gonna do is, so now, and I was stumped because I didn't understand that if we go to the Finney array, where is, okay. And if we go finally to our Finney array, I think I'm searching here in the chat. entered an invalid address. Well, I know the symbol here. Let's copy that in. Hey, Jude. Good to see you. Cool. So I figured out the problem, catching you up. So the problem was basically that I didn't realize there actually are two entries here. I didn't read the B0 and the B8. So there are two entries in the Finney array. So what we're going to do is overwrite this last one, this B8, with the address with the do write system call, and then we're going to not system call, but the do overwrite, our arbitrary write primitive, and then that's going to let us to then overwrite what happens before it, and that what we're going to do is jump back to the thing that is calling this, that's doing this. So this is going to now get us this infinite loop where now we can write and do everything that we want to do. So I was wrong. I think I thought that it ended here at B8, but I didn't realize that actually this DQ, this double quad, means that there is something there, and that's this pointer to, I guess, the Finney function. So that's going to get called first. So what we're going to want to do, so the Finney array is here, and that's what we've just, great. So address of do leak. Okay, I'm trying to remember exactly where we were. Okay, yeah, so this is so this time we overwrote the Finney array. So that's the start of the Finney array. The first Finney array is going to be Finney array plus 0x8. So that should get us to this one. And it's important that otherwise this will blow up because we're not going in the correct order. So it would, if we overwrote B0, we would not get a second chance. We have to overwrite B8, the 8 bytes offset from this symbol, because the Finney array is done in reverse order. So we're going to do that, and we're going to overwrite this with the symbol do overwrite. So we're going to get from Pwn Tools the exe, we're going to get the do overwrite symbol, send that in. So send that in, and then that should overwrite that. And then now we should get to the do overwrite again. And then, so we should be able to, so we should be able to then, okay, so let me put a comment here. Let's see, overwrite first, actually the last entry in the Finney array. And now overwrite the last, which is actually the first entry in the Finney array to get the loop. Okay, so this will send us back in a loop. So, okay. So, okay, now what we're going to do here is receive until address. And then we are going to send the address that we want to overwrite. In this case, it's going to be the Finney array dot encode. Okay, so that's going to send that, and then we will receive until it asks for the data. And now the question is, where do we want to go? So we need to basically go to, and we were looking at this before of what called this. And actually, I don't recall off the top of my head where this was, because there was two libc CSU Finney. Oh, the F string again? Jeez. I should just write a freaking, I don't know, some Emacs thing that would tell me when I do that, but thank you for that. Okay, cool. And here is where I was testing it earlier to make sure everything works. Okay. So what we're going to do here, we're going to run the exploit. We're going to set a breakpoint on do overwrite. This should give us some understanding of how many times we do this. So the first time we're doing this to change the 4 bytes on the 1 byte on the stack to loop back and to get this loop going once. Now we leaked out the second one. So now this should be the, this was the overwrite of the Finney entry. So this is the address of do overwrite. Yep, C3. That's why we're here. And okay, great. So this is awesome. We can look at then the backtrace here. So we can see that, okay, so what we do overwrite was called from libc csu fini. So that we should be able to plug into our, and if we go back here, we can see that's used here. Let's look at it in disassembly just to be a little bit nice. Yeah, so the basic idea is then what we're going to do is jump back here. So the Fini array will first let us do an overwrite and then jump back here, which will let us do an overwrite and then jump back here. And now we'll get as many overwrites as we possibly want to. The stack will be moving, but that'll be fine. So, let's, great. So now where we want to go is we want to overwrite that with, so now we're going to get the address of this. Con.send, pwn.p64, send that value. And then now we should be getting a loop. So let's verify that. And just to verify, let's do this. Let me just check any F strings. Okay, good. Everything looks good. Cool. Let's run this to see. What I want to do now is see if we hit that that again. And when I say that, I mean do overwrite. Cool. So we get there once, twice, second time, third time, and did not have that address. Okay, why does it not have that address? Import pwn. Let's see. So what I'm going to do is just grab this. Great. Okay, then I'm going to ask, yeah, I'm going to see why don't you have that? And I'm going to look. And okay. Lots of symbols. Why are you not here? Oh, of course, because it's underscore underscore. Thank you, Ida. Okay. There we go. Okay, that has the offset, and now then we should be able to just plug that in here. Underscore underscore libc csu fini. Now that should give us our loop, and let's infinite loop from here. Okay, break, do overwrite, continue, 1, 2, 3, 4, loop, and then we got the loop. Because now it's asking for our data where we've hit it again, and you can see the stack, right, is growing continually on this libc csu fini. So because we are continually just going back to this function over and over, that will be on the stack. So this is actually great. So now that we're here, now what we want to try to do is to understand, okay, so, and if we, let's open this. Wow, I really don't show that again. That is what I want to do. And the, so ROP gadget. So now the question is, what's our ROP chain? Oh, okay, there's so much stuff. Okay. And of course it's not without that. Great. So now what we want to do is basically get this ROP chain. So we have, yeah, great. Okay. So now that we have this, what we're going to do is we're going to use what we're going to do is write out this ROP payload, like let's say on the stack somewhere. And then finally what we're going to do is then pop and jump off the stack to make sure that we go jump and return control flow there. So, and we'll need to kind of essentially pop out of our loop to do that. So what we'll do now we need to get this this ROP payload into here. And the other thing that we'll need to do is fix up all these addresses. So, and really all I care about here really is the addresses. So let's, oh, this is definitely not gonna, is that gonna copy? No, of course not. Oh, you enable mouse mode, and then mouse mode comes back to bite you. Okay. I think if I enabled that stupid thing, it would copy correctly. But all right, now that I've completely lost control of my copy paste, let's do this. Well, basically, just what I'm going to do is run this in a different terminal locally rather than fixing that problem. Hello, chmodkd. Oh, if I hold shift, will it work? No, the problem is my terminal, because I set up mousing in here, but then it's not going to scroll the thing. But do I have to write each ROP address? Yeah, we're going to write each ROP address to some location in memory, and then we need a stack pivot, so the stack then points there, and then that will start executing our payload. So let's do, okay, yeah, I was just gonna do this locally, I just have the same program here, I think. ROP gadget, there we go. You can also write the ROP chain by hand. I'm just lazy. Okay. But the fun thing is, this is definitely not a format where we can actually use this payload. Oh, hey, Sala. Nice to see you. Thanks for joining. And so what I'm going to use is an Emacs macro to basically change all of this, because we need to use the base of our address. So to figure out how to do that, let's pop over here. We will, did I have IPython going? Nope. Pwn. exe, there we go. Okay, because we use address to do at the start of the address, what we're gonna do here is, so I guess we could just use this. Yeah, the problem is we need to add offsets to each of these. So first we will, okay, now we have them where we want them. Now what we're gonna do is, I'm gonna do an Emacs macro in order to reformat these the way that I want them. So I will start, okay, let's see, p equals byte string first. Okay, and let's see, actually I don't want it as a byte string. I'm going to say p is a list, because I want to add all of these to our list. And that way, actually, if I just do it like this, that's even easier. Okay, so now I'm writing my Emacs macro, and what I want to do is p64 there to there, comma, next line, bang, bang, bang. I think I missed a bin sh, so let me, yeah, always important. Pop it in there, there. So the reason I'm, so it's the ROP chain, yeah, the ROP chain is doing execve bin sh00 is what it should be doing. Or I actually think this is a better, I think it's doing data plus 8. Yeah, it's going to do an execve bin sh, and then I don't think it's going to do 00. I think it passes some of the pointers correctly, but we can test that when we do it. The reason being, you can actually get into some trouble if you try to do, because yeah, essentially what we want to do is ROP chain to do execve. The problem is, especially, and this is actually, I guess, important with DEF CON finals coming up, at least that group used to be really well known for doing using BusyBox. And on a BusyBox system, so BusyBox is like a minified kind of like user space programs. So things like binsh, ls, id, all this kind of stuff, these are not individual programs. You compile one big binary, which is your busybox, and then everything like binsh, binid, binls are all symlinked to busybox. And why this is important is it means that if you call binsh execve like this on a busybox system, it can't figure out which program you were actually trying to execute because of this second argument here. So anyway, it's just a nice thing to do. We'll see if that actually does this, and then we can change this ROP payload a little bit to make it better. And you can see this kind of ROP chain is pretty shitty just because it's so large and it has all of these add 1 to RAX returns. If I was doing this by hand, I would choose a better one. But honestly, at this point, we have an infinite number of writes, so we kind of don't care. And so we'll just do whatever we can do here. Okay, so now my payload here is a chain, is a list of addresses, and these are the things that I can write. So what I am going to do is I'm going to need to write these addresses, let's say somewhere on the stack. And where am I in this program sequence? So this program sequence, it's now, yeah, so now we've hit our infinite loop for data in P. So now this is going to go through each of these. And what we're going to do is write out each of these things. So, or hopefully write out each of these using that. So what we're going to do is make sure we use this similar thing. We're going to receive until we get an address. And then essentially we're going to have to figure out some address. And then we're going to read until data. And then we're going to do con.send. I think just data should work. Yeah, because that's a byte in there. So we're just sending each of those. And so we're going to write these out. Now the question is, where are we going to write these to? So that's why we're going to go over debug. And okay, what we want to examine is the stack. And specifically, I actually don't care about here. But yeah, let's go into here. So the problem is the stack is going to be constantly changing. Well, it's not a problem, but we just have to keep in mind, we don't want to write this somewhere, let's say below the stack, where we're going to eventually get down and overwrite. So we need to choose some address that's above the stack, and then we're just going to write it going up. So we could kind of pick any address here. It really doesn't matter as long as it's above any function frame that we're actually going to execute. And again, okay, yeah, I'm going to... But mouse reporting has prevented making a selection. Disable. I see. Now I just disabled all that mouse stuff. Just so I could. Or maybe not. Huh. Okay. Okay. So okay. So we need to figure out some address. And so actually, if we can make this easy, we leaked out. If we look up here, right, the stack, we actually leaked out that stack address. So just to test that this works, what I'm doing right now is basically just trying to figure out if this works. So let's see this stack leak. And I think that's probably going to be above, but let's see if I can still scroll. Hey, there we go. Okay, it is kind of nice to be able to scroll. Okay, so let's see. So this is asking for a stack leak. So this is the address that it gives us. This, let's write it here. 0x7ff C577B4D00. Okay. So that is the address that we leaked. Let's kind of look at where that is. Yeah, so we should, and F, so where am I in the stack chain? Down, up, okay, so I'm at 3. So if I look at the stack here, okay, B4, And then my address was B4D, so C, yeah, so right here. So if I start overwriting here, it should never, the way I have the control flow here, should never come back here. And so that's fine. Actually, I guess, I guess if we overwrote, okay. Yeah, I was thinking, well, okay, let's just test this. I have an idea, but let's just test this first. I don't like to get ahead of ourselves. And so I want to make sure the writing works and everything else works. So the address, I had some stack adder leak. There we go. And what I'm going to send is I equals 0. We need a counter here. So stack address leak. Well, we don't need that, but we need ROP chain address is equal to the stack adder leak. And then we're gonna take this, write that out. And then we need to make sure at the end of each loop, we add 8 to it. So that way we'll write over and over again. And I think then at this point, we should then have written all those addresses there. So what we're gonna want to, well, yeah, so let's then test. So what we're gonna do is run it, look at the stack leak, what's leaked on the stack, and then examine it to make sure that our ROP payload actually got leaked properly there. And we'll see if I messed up anything significantly. Okay, and I'm just gonna run it. Oh, okay, that did a lot of things. Maybe too much, but let's, yeah, there we go. Okay, so the stack leak is 7FF D6 ABE BAF0. Okay. And we can see our backtrace, right, is we have all of those libc finis here. So X 20GX AF0, and let's see. Okay. Oh. Okay, that is definitely something. So that's that. And it should F8. F9. F8, oh no, D0. Okay, the first one worked. Now, is this stack address being overwritten? That's kind of what I'm wondering. Let's see. Yeah, why isn't that overwriting? Oh, well, the first thing that should have been assigned is that what was in that location that I was looking at was the very last element, 917C, which was down here, 917C. Of course, I was I incremented the stack adder leak address and not the what I was using and not the original thing. So anyways, that should be good. Now I should see my chain, but I already noticed another problem. The other problem is, well, these are not stack locations in memory, right? And the reason is these are all P32s of these addresses. These addresses have not been offset from our address. So another Emacs macro, bang, bang. Let's see. And here I want exe.address plus there. And then P64, go to the next one. Blanket. Now that should be good. So now we should do this. Now this is calculating based on the address that we got back of where this code is located. We're regenerating our ROP chain based on that information that we get. Let's run it. All right, did a bunch of reading and writing. That's good. And let's see. So the stack address, and I could run this with stack with ASLR disabled, and that would actually make this a lot easier because I would know the stack address and I could just examine it every time. But that's okay. We can do this. C7FFC62F86E80 X20GX. Hey, those look better. So some of the things I'm noticing is that's the bin sh, and this, let's see, I found a cool way to do this. It was, I forget, but Jeff, documentation. If we go here, and of course it hasn't changed, but if we go here, then there was a command dereference. Yeah, this is a really cool command. So what this command does is it shows us like the stack kind of layout for whatever we want. And this is kind of a very nice way of looking at this because we see that these are code. So this jumps here, which jumps to pop RSI. So this puts this next one into RSI. And this next one is pop RAX, so it pops that into RAX. This then moves RAX to where RSI points to. This does pop RSI, which pops that in there. That actually, so then we can see that this is really nice, and we could hit enter to keep this going. We could pass the -L option to specify how much we want to output here. But yeah, this was something I saw while trying to like debug things. So that should be nice. So we see our stack chain here, and now so we can test that this works. Basically, if we let's see, I'll just give some input and stop executing here. So now I just read something, so I'm in read int, I'm in do overwrite. And let's go here. So now it's going to ask for my data that I want to read. So let's go 0. So, okay, right at this point. So now it's going to ret. So if I, let's see, I think I can just set RSP. RSP. So here I'm just pretending, hey, what if I change the stack so that it points to here? So if I x10gx $RSP, now that my stack, and of course I've changed this in the debugger, so this won't fly. But if I do SI, then I can see I go pop RSI, ret, pop, ret, pop, ret. And if I keep doing this, yeah, beautiful. So then I get a, process is executing a new program, user bin dash. This is because on this machine it's been changed to bin sh is a symlink to bin dash. So what this means is I executed my shell. So this is great. This means my ROP payload works. Now the only thing that we need to do is, now that we've written everything, we need to basically exit this loop and actually get out of here. So how am I going to do that? I think I'm going to be pretty clever here. So we had this function, and I'm going to run this exploit again. Basically what I want to do is jump back to after all of these calls on the very last one, so that way we start cleaning up the stack and we just start returning. Yeah, so one thing I could do is overwrite the Finney array to redirect, but I need to redirect control flow. The problem is I need to control the stack, right? So I need to control where the stack actually points here. So there's a couple things you can use. Actually, yeah, let's we can do that. So one of the things, so there's a couple things we could do. One of the things we could do is figure out how to pivot the stack. Exactly. So the problem of why that's tricky is what we'll need is a very specific gadget that will adjust the stack pointer exactly how much it needs to go in order to get to where our payload is. My idea was change it to basically jump back at the end of the libc CSU Finney so that all of our frames just start returning, return, and then our stack will go there. Let's do that. Let's do that first, prove that it works, and we'll go back and do it the other way, because I think it's good to explore different ways of doing things. So what I'm going to do here is set a breakpoint right at that function, and I want to go right before the prologue, the leave ret, so that leave rets, and then it jumps back and back and back, but I need to know exactly where to go here, or I need to know exactly where to write the stack. So what I'm going to do is overwrite the saved instruction pointer of that very first libc CSU Finney. And so that's where we are right now. So next instruction, push. Okay, now it's going to go there. So before you do that, I'm going to examine the stack, GRSP, and backtrace, so I can actually cheat a little bit because this already got me here. So 160. So so if I start overwriting here, once my function frames return, then I should start executing my payload, because that's the ROP chain. So I'm overwriting essentially the saved instruction pointer of one of the frames on the stack, and then I'm going to force it to go back. So let's go here. So now the question is, I need to figure out that address. So libc CSU Finney RIP saved RIP is going to be some offset of this stack address leak. So what I need to do then is figure out where that address is. So this is my stack address. So my leaked stack address this time is 0x7ff D1E4942D0. Okay, and if I x 10 giant X, that will just show me there. And because I don't trust myself to do math, so what I want to do is then, what's that delta here? So that's the address I got leaked. The address that I want is 77. Where were you? There you go. 77 7FF DE D1E494288 because of that second one. And so that's 48. So I always verify because I hate doing these offsets here. And let's examine x.1 gx. Good, that's the address that I want to overwrite. So that's the saved instruction pointer of this first libc CSU Finney. And so the offset was, so if I take the leaked address, the 2D0, and subtract 0x48, that will be where I want to go. And let's do there. Oh, so that's actually the address. So that is where I want to start overwriting from, not the leaked stack address. So that's what we're going to start overwriting, and now we need to make it return there. So now what I'm going to do is, so this, does this have a return? Oh yeah, jump to term proc. Oh, term proc is actually the one. Yeah, so all I'm going to do is break out of this, or I guess, I get other ways you could do is like overwrite this with one of the entries, but what I'm going to do is change. So okay, let's do that. So now we've overwritten properly that thing, the saved instruction pointer of libc CSU Finney, and now we need to make this function basically return. So one interesting thing is, so we can actually, because all of these will be on their last call, so they're all done. So what we really need to do is just send it here. So after this call to this element, so we're basically just going to say, but it is going to call. Okay, so it is going to call. Okay, so a call can just be done by a ret. So any ret that we see, we can just return there. And so that means when it calls, it will just return. It's basically like a no-op. There should be like hundreds of these. Why are they're not? We can actually even figure out one just from here. But let's, yeah, where is a good ret? Just one ret. I think that should be good. Okay. Okay. Now overwrite the looping element. Overwrite the looping filling element with a nop, which just returns. And there we go. Our address is going to be the Finney array. Now, the real question here is how many times. So we don't know which one of this increment we're actually at. It may be the first time, it may be the second time. So we are going to get the overwrite that and just send ret address. Now I'm going to do connection.interactive because I have actually no idea if I need to read an address one more time if this next one is going to go, because we're on the first. Oh no, we are on the first overwrite, so this definitely should work. Well, theoretically should work. Let's see what happens. Oops. Stuff happens. Int object is not iterable. Okay, cool. Oh, of course, because I didn't p64 that return address. Okay. And I keep closing this. Okay, run. Hey, there we go. Awesome. Okay, process executing no program, user bin dash, amazing. Okay, so let's figure out what actually happened. So why that worked. Or debug it to show kind of what it did step by step. And then we'll go back and do it the other way. Oh yeah, well, let's make sure I this did work. And then, yep. Okay, cool. So I did get a shell on the other one. Whew. All right. So, because I hate it when it just works like that and we don't get to actually debug anything. It's always, you know, I never trust anything that works right on the first try. But that was pretty sweet that did work. Okay, so let's, man, but it is always, if this was a CTF, you like never worry why it worked or didn't work. You just go back and and do it again. Okay, so what I want to do is, what I really want is that address. Now, how do I, would be a good way, oh, duh. Okay. So I'm going to add just a little debugging here. I'm going to write this out, and then I'm just going to add this like a classic CTF cheat. Well, not cheat, but a tip when you're debugging your own things of saying, hey, actually putting an input here means your exploit script is not going to send that final payload until you hit enter. And so then it basically waits for you to set everything up. All right, let's do that. Run it. Cool. And it gave me the exact address to break on. So I'm going to do Control C in here. And BT. Yeah, so this is crazy. So when I do BT, I actually know that I've done this right because we see all these libc CSU finnies, which are all of the stack traces, all of the, sorry, the stack frames that are on the stack followed by, well, what's the next one? Oh, this is our ROP payload. So actually this tells me that this was done correctly, except that or at least that I'm writing everything on the stack correctly. The problem, of course, is how do I know that this actually worked? So let's set a breakpoint right here. So now the next thing should be overriding this with this ret. And so, okay, continuing, it's waiting on the input. So we need to do that, hit enter. Cool. Okay, so now we redirected the last entry of the Finney. So let's, what I want to do is show that. So x2 giant x, cast it to its declared type. I don't really care. Just give me that. Yeah, there we go. So this is where I break. So this is the address of do overwrite that we were calling again and again. And this is this 0b, which is this last ret. So once this ret is called, it's as if we just called nothing. So we called something and then returned right back. So if I go next, then we should jump right back to the end of libc csu Finney, which is here. So now it basically just finished its second call. So it did its first call. It's doing its second call. It's going great. We're cleaning up. And now pop, jump here. So this is actually going to jump to a different thing, which does nothing and then returns. So then this is now jumping up the chain here. And I'm just going to keep kind of stepping here. And this is basically popping off each of these function frames off the stack. And if we do this enough, at a certain point, we'll see our chain getting closer and closer because, and again, we had each of these calls for every single write that we did. We had another one of these calls. So this is going to step. Oh no, am I pulling a yawn? I thought this would be done quicker. Oh, there we go. Okay, we're almost there. So we can see in this stack diagram that we have our payload here. And we got there. And finally, this is the second to last one. And now here, yeah, so now if I look, my stack should be, yes, the stack is exactly what I made it to be. So this is why this works. So, okay, great. Now this works. Now let's look at the other way. And mainly I wouldn't just do this just for fun, but I actually do want to practice getting better at doing the stack pivoting stuff. So I want to, we'll basically write it to an arbitrary location, and then that'll pretend like we have our data somewhere on the stack, and then we're going to try to pivot to that data. So what we're going to do is change this. The ROP address that we're going to go to is the sorry. Okay. Yeah. Just where so now we're going to write everything to the stack address leak. That's what it was. Okay. So we're going to just change everything there. So now we're writing back at that stack address leak. So now it's not exactly at the right place. So we're going to need to change the stack for this. So let's do a, okay. So now, and then where are we going to, so now here, instead of returning from to this ret address, so rather than returning here, we're going to need to find a pivot. Need to return to a stack pivot gadget. And so what we're going to do is figure out exactly how we want to do that. And I'm going to use the same trick of saying, okay, well, what, so it's not ret address, but I need stack pivot adder, and that'll blow up. So I just want it to blow up, but I'm going to change this to be stack pivot adder. And I'm going to comment that out. Cool. Okay, so what this is going to do, now I'm going to figure out how to pivot. So and to help make it easier, okay, great. So to help make it easier, before I pivot, I'm going to print out a hex of where the RUP chain is. And then what we're going to, now this will let us breakpoint, and this will let us understand, okay, from where we're actually going to be, how do we need to adjust the stack frame here? Actually, what we could do is so the stack pivot address, I have nothing, but let's actually go back to our ret gadget, and we'll see that this doesn't work. This will actually just exit the program. Actually, it'll probably break because we've overwritten the stack. So something will definitely break here. But what this will do is give us a way to set a breakpoint right at this place, just like we did before, and then figure out what the distance is between the current stack and where we need to go, and then figure out another gadget that will actually get us there. So there's the stack pivot address. I want to print that out. Actually, and we can use a nice thing about one of the really nice things about F strings, if you know how to type them in correctly and include the F, is this equal sign at the end, which shows you what you're actually printing out. So that way, when things are confusing, RUP chain under. There we go. And that way it'll show you. Okay, see you, Jude. Yeah, so now you see, like, it's really cool. It shows you what it's actually printing out. So this is like easy for debugging, or a lot easier for debugging. Okay. All right, so now we can set a breakpoint. So what we're going to want to do is set a breakpoint right at this stack pivot address, because this is going to be the wrong address. Copy. So x10gx. Okay. So that is where we wrote all of our... No, that's the stack pivot address. So this is where we want to break. B star. And the other one is our RUP chain address. Okay. And now that we have that, we can just examine the stack to make sure that that's correct. Okay, it is definitely not correct, because we printed out RUP chain address and not our stack leak address, because that is more useful. Okay, well now I need to redo this. Boom, boom, kill, rerun. All right. Okay, so break on this fake and incorrect stack pivot gadget, and print out this stack. X10gx. Great. Okay, that is my RUP payload. Whew, this is why you always double check things. Okay, so I have that address. So now I need to figure out, so let's continue. And we right here. So now that I've set this breakpoint, I'm right at this ret. So this is the start here. And what I'm going to do is print out x10gx $RSP. So what I want to know is, where am I currently on the stack? So I'm at this memory address here, D8. I could also do p/x $RSP. But where my RUP chain is here. So what I'm looking for is, after this gadget, I want the stack pointer to be pointing here. And that will mean that this, when this gadget returns, it's changed the stack such that it starts executing from where I want it to execute. So looking in here, okay, so what's the difference between those two? Minus $RSP. Okay. Okay, so A08 is my delta. So let's see, how big is that? And just to verify, so what I want to do is RSP plus 0x-A08. And that gets me to EE0, which is where my payload is, which I just looked up here. EE0. Great. Okay. So now we need to look for ROP gadgets. So there's Ropper was a tool that I was using before. One of the tools. So there's Ropper, ROP gadget. Ropper I've heard is really good for this sort of thing. So that's why we're trying that. And if we look at the help options, it's got a nice stack pivot options. So what we're going to do is just look for gadgets which change the stack pointer. And what would be perfect is if I basically had a gadget that said RSP plus A08 ret. And this would mean that it would adjust the stack exactly where my payload is and then return. So that would be perfect. Let's look. I have absolutely no idea how. I haven't prepared this, so I have absolutely no idea if we're going to get lucky. Okay. A80. Okay. Well, we didn't get that lucky. That'd be great. Another thing we could do is look at the registers. Just in the offhand chance that maybe something useful is in one of these registers. Doesn't look at it off first-hand glance, but so for instance, so we do have some things that actually do change, the stack pointer. Like here, this is add 10 to RSP. So what I'm going to do is first filter these by just those that have some add RSP, and that will help us like narrow down a little bit. So here's like add RSP 90. So this gets us 90. Oh, wow. Oh, and I guess I could. And then I can look in here for. I could write a script, I guess, to like extract all these. Here's 90. Yeah, A80 is pretty it's pretty large. Is kind of what I'm worried about. I actually don't know if there'll be a ton of let's see. $68, $58. 1D0. Hang on a minute. And where were we? AD0? A08. So I don't have A08, but I do have, I guess I should figure out what the largest one is and then figure that out from there. So 1D0 was pretty good, followed by a couple pops. So these pops will all change it. So this will be AD0 plus 8 plus 8 plus 8. 18, B0, 20, 20, 10, 20, 10, 148. A0. I'm looking for 0A. Yeah, okay. So let's see. And nothing there. A0. Yeah, I'm just trying to see if there's any. Oh, A03. Oh, that's pretty great. Now, I've actually been meaning to run an experiment, so let's do that right now. I don't remember how these addresses after, like, arguments to a ret instruction actually work. So when I don't know that, then what I'm going to do is run a little test main move 0 into RAX 0, call test and I don't know, move into RAX 1 and ret 0x A03 just to see what happens. Let's see, sub RSP 0x A03, just because that will probably mess it up. Cool, and this will then allow us to test. So GCC test.s. Intel, just use Intel. GCC. Yeah, it's a directive. That's right. GCC. And there's definitely. Where's the directive? Okay. There we go. Intel syntax, no prefix. All right. So this will tell GCC that we want to use Intel syntax. Undefined reference. Oh, global. Dot. All right, great. It dumps, but that's good. That's what I want. Oh, and let's just to make it easier, make sure we get everything, and make sure, again, let's disable optimizations. All right. Oh, I want to GDB it that time. Okay. Great. So run it. Okay, this will be very simple. Subtract from the stack pointer A0, move this, call test, move 0 into RIX, P/X $RSP is our RSP value. I'm going to copy that for now. And now this ret A03 will do, okay. Okay, so I think it must change the stack and then do a ret is my guess. So $RSP. Yeah, AB0. So it changed the stack pointer by A0B, which was almost, our thing was A03. Oh shit, is this really close to what we want? A08. Oh, it's not even aligned. Shit. Oh, that's going to cause problems. But okay, let's. We're just thinking through this. Okay, so it must. So these ret instructions must return first. Well, maybe not first. Yeah, it must be. No, they did a ret. Okay, yeah, so that's not going to be useful because we don't control the stack pointer. Okay, so what this did is, yeah, so this brought us back here. So this brought us back. So it did a return and then, so which changed the stack by 8 bytes. And then it added whatever the argument was. So it still does that ret. It just then changes the stack. Okay, so I see how you could use that. Okay. A8. I'm looking for any A9EB, A0E9. Is that close to what we want? Is that way too much? A08 is what we want. A0E9. ABE Okay, but now these rets are not good because add 8. Okay. Yeah, I mean, I think I could see how to put these together to work it, but okay. So what's my largest? I feel like adding is pretty easy. The problem is there's so much on the stack between where we are. Okay, so starting with an add 90. Let's do this. Grep at the start. Hello. There we go. So everything that starts with that, and just 1,000. That's interesting. I guess I technically do like know where I could go from here, but just to complete this, I want to see what these adds are. So, there's a lot of different ways to do this. Let's see. I could cut based on a delimiter of semicolon and get the first one. Yep, and then cut the comma, get field 2. Sweet. And then so now I can actually see all of the potential offsets here, and I could like sort it, unique it, do kind of anything right here, but there's some pretty good ones. 278, nothing. Actually, this is interesting because this is bigger than a byte. So there are some pretty decent ones here. Like this is 1,000, but there's nothing that gets us kind of exactly where we wanted to go in here. So hey, let's cheat because we can. Now 1,000 probably won't work. So what we can do is we can technically write this anywhere. The problem being that if we write it somewhere incorrect, we'll overwrite and kind of change the stack there. So yeah, if we overwrite it too low on the stack, then that will mess up what we're trying to do here. And sorry, it'll mess up the stack. So we'll be writing down to the stack as we're kind of reading up, writing our payload on it, which will be a horrible, horrible time. So 148. Let's see where we are there. I suppose we should figure out where the stack pointer of the first, no, don't kill window. Uh-oh, that's the wrong. I was like, where are we there? Okay. Yeah, this 78, this is where anything we start writing under that is the problem. So let's see, maybe we just get lucky. Okay, I don't want to press up a bunch of times. Help up. Okay, help up. I don't know, we're at 1 and I want to get to 78, so 77, I think. Yeah, great. Okay, let's read the stack here. So this is at that stack address at 79E0, and the address that we have. So our stack address leak is at EE0. So ED0, this only gets us, oh, dang. Down 77. (9A8). Okay, did that get us any closer? Anything within 9A8 that we could play with? Let's see, just on the offhand chance. Is this actually mapped? Because I'm worried that it's not. But if it is, then great. Then we don't have to worry. P/X, no, X, then giant X, $RSP plus. Well, that looks fine and dandy. Why don't we just put our stuff there and then we'll jump there. Of course, let's look now that we're going to use this. We need to really inspect this gadget. Inspector gadget. Inspect this gadget and colon add RSP OX 1000. Yeah, because it's not exactly at 1000. So this is where this gadget is. So let's copy this. Okay, so now we need to do two things, right? I'm going to have to change where we're writing and change where we're going to. So the stack pivot address is going to be here. So this is going to be at offset there. And what this does is oh, there we go. Figured out how to do it. Yes. Okay. Oh, that's going to save me time. Okay, great. So the stack pivot address. So what happens after RSP? So after stack pivot, RSP is, let's see, plus 0x 10,000, and then it moves whatever R12 into RAX, don't care, and then another pop, so plus 0x8, and then something will be put in RBX, which we don't care about, and then plus 0x RBX, and then RBP, so another 8, plus 0x R12. Okay, so that's 3, pop, 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 3 pops. So, and then the ret will go to our return pointer, so our return address. So what we need to do here is make sure that where we write there is where we want to be. So our target address is, in this example, this that is at RSP plus 10,000, but we actually want RSP plus 10,000 plus 0x8 plus 8 plus 0x8, so 3. So what we really want is here. So target address. So we need, so now we want to be, now we're not going to write at the stack leak address. So write out ROP chain at RSP, blah, 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 which is, in our case right now, it's this, and specifically from the, yes, the stack, so P/X, that's where I want to go, and I want an offset from the stack address leak. Great. 610. So this is the stack address leak plus 0610. And that should give me the address that we want our ROP chain to be. Wow, I really hope this works. Now, I think that should work. Let's see. Okay, cool. where were my prints? I want to make sure. Yeah, the stack pivot address and the stack. Oh yeah, I'm not writing into stack adder leak. I'm writing into I realize I don't have a good way of capturing that, so let's make a variable quickly and then print that out. That'll help debugging. All right, now it's waiting for our input. So now let's check it. So now at so x 5i, so I'm going to inspect. Yeah, so this is my add 1000 to the stack pointer and all that mess. And then this is where my ROP chain should be. So x10gx, we've seen this enough. This should be very clear. Yep, that's great. So I got all written there. Now what I'm going to do is set a breakpoint on this address. So break, continue, and then hit enter in here. Okay, so now I should be here. So now this is my stack pivot that's changing my stack to then point into where I want to be. So let's next instruction. Okay, so add 10,000 to the stack pointer. Oh, let's just print it out. $RSP. And then print it out. Boom, boom, pop, pop, pop. And then a ret, and then x10gx, $RSP. That looks like our ROP payload. Boom, there we go. Who am I? All right. Wait, did that work? Yeah. It did work, right? Wait, let me. Why does that feel like it didn't work? Yeah, there we go. All right, so there we go. Pop the shell. And so now we just did this in two different ways. By essentially putting our ROP payload exactly onto the stack where it would be overwritten. And then the second way was trying to figure out where to jump to in order to get everything going there. Awesome. Oh, that was cool. But that, of course, then caused us to then change where we put the stack pivot. So a question could be, what if we can't control necessarily where our ROP payload goes? In this case, we jumped right to the start of our ROP payload. Another trick is to, you could, the concept comes from like NOP sledding. So executing, basically, we could extend our ROP payload maybe down. So rather than going right at the start, we could jump anywhere in the start of this ROP payload. And that's just with a bunch of addresses that point to a ret, right? In a stack, in a ROP payload, a ret instruction basically just does nothing and moves the stack up. So in this way, if you had a ROP pivot that pivoted maybe partway through your ROP payload, you could actually deal with that by putting in NOPs and everything would be fine. Okay, awesome. Cool. All right, well, that was the end of onewrite. So thanks to the Insomni'hack folks for doing that. And I think with that, I am going to sign off. And I think the next time I'll see y'all is after DEF CON, but I'm going to keep doing these. So hopefully you enjoy them. Bye.